Hello everyone, this is Michael Breddy, founder of Applied Ion Systems, and thank you all for attending this live stream. Got a little bit unique viewing tonight. Usually when I do live streams, it's live propulsion testing or debugging or qualification of a thruster. But tonight we got a special unboxing of the brand new thruster system that I'm working on. This is for the ADAMANT Series AIS-EHT1 Micro End-Hall Thruster. For those of you who have been following this effort, this is my most advanced thruster build to date, and the first Hall thruster for the Applied Ion System effort. I want to give a quick shout out to all my supporters, contributors, patrons, and everyone who's really donated and contributed to this effort. It's been a tough journey, but it's really all your contributions have really made it possible for me to continue developing propulsion and getting to the stage of where I'm at now. I also want to give a quick shout out to Xometry. All the parts that you're going to see here today, which is all the 3D printed parts and all the machine parts that I'll be unveiling for the thruster, has gone through them, and so far I'm really happy with the services. The quality and lead time and everything has been really excellent, and has really been pivotal in all the systems that I've been working on so far that I've used 3D printing and machining. So I definitely suggest checking them out for those types of services. Now, I don't know actually what to expect. This is the first time I'm opening up these parts, and these are the major parts for the thruster. So the thruster itself isn't assembled, but I'll be walking through a lot of the basic components and showing kind of the sub-assemblies involved for this particular thruster. The live chat is open, so you can actually ask questions during the chat. I apologize if I miss some questions. There's going to be a little bit of lag between the time I present and when you actually see this video, so I apologize for that. So let's get to it. So just as a brief overview, the AIS-EHT1 is a micro Hall thruster that I'm currently working on. So this is, you can kind of see the CAD renders of two variations of this thruster. So this thruster can support either neutralizer filament or hollow cathode filament. I did this because it gives the system a lot of versatility, and I will be explaining later on some of my design choices and why I selected an end-hall thruster versus the traditional, very common stationary layer. The filaments allow for very quick testing and allows it to be dual purpose as a standard ion processing end-hall source if needed, where the hollow cathode neutralizer allows for more for the propulsion side aspects of it. But both allow a lot of flexibility with the system and allow me to explore a lot of things. Now, the ADAMANT series is a whole development which explores the use of very small scale, highly compact, highly integrated micro ion and plasma thrusters for small Cubesats and hopefully down to pocket cube size systems. So one of the key aspects of this thruster is, or this thruster series, is the use of Adamantane fuel. If you haven't heard of it, most people haven't, and I only recently discovered it several months back. Adamantane is a type of diamandoid hydrocarbon. So it is a very interesting substance because it allows for fuel delivery as a solid form. So the fuel itself is stored as a solid. It actually kind of looks like a granular salt or sand, and that sublimates at very low temperatures. If you've seen any of the testing with the ADAMANT series test cell discharge, you'll actually see that I'm able to sustain stable glow discharges in vacuum at very low temperatures, so 12 to 15 C background temperature for sublimation, so not even any heater applied to the test cell, and being able to ionize at power levels less than a watt. So it has a lot of exciting potential. It's actually very similar in many aspects to iodine fuel. which is being looked at heavily in the propulsion field. They both have very high ionization cross sections, making them very easy to ionize. They can be both stored as solid fuel that is sublimated, so they're unpressurized fuel. One of the major differences, though, or a couple major differences, is that adamantane is not corrosive like iodine. Iodine eats most materials and makes it very challenging to work with from a materials perspective. And adamantane is also significantly less toxic than iodine. Originally, my plan was to go with iodine thrusters in the AIS-EHT1 series, which has been retired, and I moved on to adamantane due to the exciting potential of this fuel. Currently, I believe that Applied Ion Systems is the only electric propulsion company in the world actively developing adamantane-fueled propulsion systems. So it's a kind of a very unique development, and there has been work for adamantane systems in EP and in the literature, but there's very, very little data. There's almost no data on this type of fuel in the field, and even very little data just for the ionization characteristics. It has been kind of dismissed by major groups, but for my needs, it actually is one of the key contributing factors to allow me to scale these systems at such extremely small levels. So kind of just before we get into the actual unboxing, we'll go over some of the basic subsystems. So I have posted this stuff on Twitter before and kind of just review it again here. So the first key aspect of the ADAMANT series is the fuel system. So there are two assemblies to this. You can see there's the heater cartridge. So it's just a ceramic metal heater cartridge that goes underneath the fuel casing. So this fuel housing holds about 3 grams of adamantane fuel. There's a spring and a pressure disc that presses the solid fuel grains into the bottom plate of the cartridge, which compresses together. And heater power is applied to sublimate the fuel and directly deliver it to the thruster. So this design allows me to scale the tank size very easily and readily. And this is the smallest tank size, again, 3 grams capacity, which makes it just easier and simpler to work with in the very beginning. So the sublimation aspect has been already tested in vacuum, not with this particular cell yet, but that will be coming up soon. The next aspect of the build is the fuel valve. Originally I was hoping to make the system valveless, but I found that adamantane actually sublimates so easily in vacuum that it really makes it very challenging for my vacuum system to keep up. So I need some valving in order to be able to control the fuel flow to the thruster. So here you can actually see a prototype valve. This is going to use a piezo element. So there's a bender element that sits in this cavity, and the actual assembly just snaps together. There's just a few indexing points, and so the tolerances are pretty tight to keep the valve assembly there. And you can see that this whole module will actually fit directly on top of the fuel tank. So again, the big key aspect of the adamantane or the ADAMANT series is very, very tight integration of the system. So the entire thruster design here you see is the fuel delivery system, which includes the fuel tank, the fuel valve, the thruster, and the neutralizer, all in one form factor. So everything is actually bolted together as a vertical assembly, making the system extremely compact. So the fuel valve will sit on top of here to deliver the fuel. The fuel valve itself will take very low power, about less than a watt for the piezoelectric drivers. The heater is rated to up to 19 watts of power. However, it's not really needed for that high power. I found that adamantane is sublimating very well, even down to 12 C temperature. So it looks like I can actually get away with even lower power levels than expected for this build. So a few more kind of aspects of the build before we get into the unboxing. One thing to note is that this Hall thruster is incredibly tiny. Normally when you think of Hall thrusters, you think, these really big systems being tested at NASA or ESA, or, the really big nested Hall thrusters at many kilowatts of power. This series is focusing on the ultra micro scale of Hall thrusters. So the EHT1, the one that I'm unboxing now, is a 10-watt class thruster. So that 10 watts covers everything for the discharge power, the neutralizer, and the heater supply. And another thruster that I'm working on, if all this checks out and looks good and the initial tests are successful, the next thruster in the series, the AIS-EHT1, which is an anode layer Hall thruster, will be looking at scaling down to the 5-watt class. So we got some very exciting small scale builds for Hall thrusters in the works. And again, this is a very, very tiny system. This isn't the smallest Hall thruster that's ever been designed in terms of the actual size of the head. There have been smaller ones. However, in terms of completely integrated system, this is probably the smallest. This will be the smallest complete Hall thruster out there. So for this current assembly with the 3-gram fuel capacity, it is 50 millimeters in diameter, and with the thruster, it's about 50 to 60 millimeters high. So it's around 1/8 of a U in CubeSat size. And with the electronics, I'm looking for the total system to be around 1/5, 1/6 U. So it'll be a very compact, very small system. So now that we've kind of gone over those basic things, let's start unboxing the parts. So I know that this guy here is going to be the main thruster, and these guys are going to be some of the smaller components, which I will go over in kind of the different assemblies for both the Hall thruster as well as the hollow cathode neutralizer. So let's start unboxing. So one of these will have just a single part, which is just a connector piece for the anode feed, and the other one will have a lot of parts and pieces for the other assembly. So this looks like it's the smallest piece. So let's just break this open, and I am going to be handling these with my bare hands. When I do the actual thruster assembly, I'm going to obviously be using gloves and washing with acetone and alcohol and prepping it for vacuum. But for now, it just makes it a lot easier to handle with the bare hands, so no need to worry about that. All right. So, and it's always a bit of a challenge, kind of seeing this stuff as CAD. It looks much bigger on the screen, and then when you actually start seeing the entire system together, it's quite surprising how small. And sometimes I even think this is going to be a little bit ridiculous to work with. So here is one part. You might not be able to see it, but this is actually a 080 little threaded clamp. So this actually fits right into the anode assembly. So if you look back at the pictures, there is an anode feed here for the thruster, which the power for the anode goes in. And the anode feed was actually the most challenging aspect of the entire design. Getting all the pieces together and insulated and fit properly was a major hurdle in this particular design. So the little piece fits right into the housing, and that is literally just a clamp that clamps the feed wire that it will be either brazed or welded to the anode that goes through the insulated feed through on the side of the thruster. And this little guy caps off on the top and fits right to the side of the anode feed. So we'll just put this to the side and move on to the next parts. So this is where some of the main parts start coming in. So we're looking at the key components of the thruster, as well as the neutralizer, which is also a bit of a unique neutralizer development as well. It's a rather unconventional design in terms of Hall thruster and ion thruster neutralizers. So let's see how these guys came out. Should be just a few parts. Again, these are all going to be really tiny, so I apologize if it's difficult to kind of see them on the screen. And hopefully after all this, I will get some close-up shots and post them on the AIS Twitter. So before we get into the main thruster, why don't we go over the neutralizer design. So here is actually the threaded insert for the hollow cathode neutralizer. So this neutralizer is extremely tiny for a hollow cathode. So you can see this is actually the hollow cathode piece. So there's a little gas feed on the side, and this is the cathode feed and the threaded feed in the back. Now this is the actual hollow cathode housing. So this is the entire hollow cathode. Again, an extremely small system in order to make this as compact as possible. This is actually printed with Somos Perform. This is one of the newer SLA materials that are available from Xometry. This is a ceramic embedded resin, and I've found that it actually has higher temperature and tolerances and dielectric strength than Ultem. On the tank housing, this is actually printed from Ultem 1010. And the nice thing about the SLA is that you get very, very good tolerances. I already checked this guy out and the fuel valve out, and the tolerances are absolutely spot on. So I'm hoping to eventually switch to all my parts to this SLA prints for the future once they pass vacuum qualification. It is more expensive than the Ultem and some of the other materials, but the material properties are right in line for what I need for this build. So the hollow cathode assembly itself, you can see here. So this is kind of the cross section of the hollow cathode. So you have the small metal hollow cathode piece here. And one thing that's very unique about this hollow cathode is that traditionally in electric propulsion, you have some sort of heated hollow cathode assembly. So there are heaters around some sort of dispenser material, either lanthanum hexaboride or there's a barium oxide, which have very low work functions and allow a lot of electrons to be released at once they're heated. So it's a very easy and common material for high current electron sources. So you see this type of stuff in particle accelerators as well as hollow cathodes. And there's two types of modes. There's either heated mode where you have external heaters, and you also have self-heating mode where the plasma discharge actually sustains and heats the insert material, and that allows the electrons to be liberated and ionize the gas for the plasma output for the electron extraction. Now, those materials can be quite expensive, and on my current budget, it's very difficult to do. And the other aspect is that you really need to run these with inert or noble gases. So xenon, argon, things that will not poison the cathode material. So these special cathodes are very low work function cathodes, but they require pure gases to operate so as the ways they're not damaged or destroyed during the discharge process or from the gas poisoning itself. Now, this particular cathode that I'm using, this is not something that's actually used in electric propulsion, but it is very common in the particle physics field. This is a cold hollow cathode discharge system. So there are no heaters. This hollow cathode works at a very high voltage, so 500 volts to a few thousand volts. Hollow cathode systems can either be DC or pulsed, and they can be operated at hundreds of thousands of volts and can deliver hundreds of thousands of amps or mega amps of current for the biggest systems out there. But one of the key aspects of these types of systems are that you can really run them on any gas, because the material that the electrons are extracted from is not a material embedded in the system, in the cathode itself, but rather the plasma. And the plasma has essentially zero work function. So it allows you to extract huge amounts of electrons very, very easily. The cost is you have to operate at higher voltages, but on the other side, I can run any gas that I want, and I can also operate this at very low power levels. The discharges can be sustained as long as I kind of meet the Paschen curve requirements for the particular discharge. One of the challenging things about this build with the adamantane fuel is that I don't actually know the Paschen curve for adamantane because there's almost no data on it in the field. So I kind of have to play around and do some initial testing and estimates. But it seems like it is very easy to sublimate and ionize with very low quantities of power, which is very good for this particular build. So for this build, we have the hollow cathode. There is a ceramic insulator, and then there's an anode. So you can actually see ceramic piece here. All the ceramic pieces for this build are just off the shelf from McMaster-Carr. That's one of the key aspects of going with this particular technology with the end-hall source versus the stationary layers, that I could avoid custom ceramics, which would be a huge killer on the budget. Discharge, the gas flows up through the hollow cathode into the feed, and a discharge is initiated between the hollow cathode and the anode. And in this particular setup, I can actually either run it in low voltage discharge or high voltage discharge mode. So in high voltage discharge mode, you can just sustain a discharge and electron emission at higher voltages, several thousands of volts, between the hollow cathode and the anode. In low voltage mode, you can apply a lower voltage for an initial discharge between the anode and the cathode, and then at the output you have an extraction electrode. So some positive biased voltage is applied to this that actually creates a field which draws the electrons out from the plasma. So I'll be experimenting with both of these types of configurations for this particular design, which allows me to play around with a lot of different extraction modes and see which one will actually work best in terms of ionization and neutralization for this particular design. So we have the hollow cathode housing. So this little guy fits right into here, and I might have to adjust the output or the feed through portion on the back, and tap that for this particular size hole, because I size these tolerances very, very tight. So this isn't quite a solid feed, so I won't be able to put that in there right now, but essentially the ceramic insert would go over the top, the extractor would go on, there would be another little insulator washer that fits over the top of that, and then we have the housing top that fits right over it. So I haven't actually received, I'm still waiting on the final parts for the system, so the extraction electrode, the anode, but hopefully that stuff will be in by next week. Those are really the last pieces, and those are being laser cut. So that's kind of a basic overview of the hollow cathode system. And again, this type of hollow cathode isn't really used in electric propulsion all that much. So this will be a very unusual build in terms of Hall thrusters. However, it'll allow me, the key and crucial thing of this particular technology is that it'll allow me to run a hollow cathode neutralizer at extremely low power levels. I should be able to operate it at a watt or a couple of watts of discharge power. So it allows me to have relatively decent electron beam neutralizer extraction at extremely low power levels. The other side of the build, which has the tungsten filament neutralizer, is that's a bit that requires a lot more power, and it's a very short lifetime. So hopefully this will give me a long lifetime for actual orbital missions. So next we're actually going to start getting into some of the actual Hall thruster parts. So first we have, well, first I'll actually just go over the design. So this is a cross-sectional view of the Hall thruster. Now I went with an end-Hall thruster as opposed to the stationary layer because it has allowed me to scale this type of system down to extreme levels. For the stationary layer, that's the classic. When you look up Hall thruster pictures, you're going to see kind of that ceramic channel with an outer and an inner shell where the discharge is held, and then you can either have a nested hollow cathode on the inside or an external neutralizer on the outside. And that would require some specialized machining. And I've been banging my head against the wall for a long time trying to figure out how to scale this stuff down. And a stationary layer just wouldn't work for me with my particular resources available. There is a variance. There's the cylindrical layer, or the cylindrical Hall thruster, which gets rid of that central pole portion and kind of has just a cylindrical open body. So that's actually being actively explored in a lot of areas for kind of low power Hall thruster technology in the 50 to couple 100-watt range. Unfortunately, that also would require me to do some modification or custom machining of the ceramic insert, which is, again, a little bit outside of where I'd like to be in terms of budget and complexity. So I wanted to design a system around off-the-shelf ceramics and kind of tailor the machine parts to that. Now, there are actually, outside of the classic stationary layer, there's several other types of Hall technologies that are actually very, very common in industrial processing. So the two common ones that you often see in ion beam processing and technologies like that are end-Hall ion sources and anode layer ion sources. So both of these do not have a ceramic lined wall. They are both conducting walls. And they operate similar principles. For my purposes, it's allowed me to, again, scale this technology down to really small levels, making it really compact without having to worry about much custom ceramics. And the nice part about these systems are they're also very robust. They're often used both with noble gases as well as reactive gases, because there's a lot of reactive gases used in the well, let's see, hold on, I think maybe with just got a notice on the YouTube that maybe there's an error with the live stream. It seems like it's still going, I think. So let me just actually quickly check out what's going on. So it looks like there might be a little bit of lag, so I apologize for that, but it looks like the live stream is still on. So again, I'm exploring the end-Hall source for this particular technology and the anode layer source for the second Hall thruster build. So here there's the actual outer casing. You have the anode feed. You have a gas distribution baffle, a couple of the ceramic washers, and then the anode, and then the upper pole piece itself that connects and creates the magnetic circuit. And I'll get more into those details as I actually unbox and show the main portion of the thruster itself. So kind of the first major component for this in this assembly is the gas distribution baffle. So the gas distribution baffle is exactly what it sounds like. So you can actually see it's this little piece here. So it's the first piece that fits in right around the central pole. And what this does is it distributes the gas where it needs to go inside the Hall thruster system, as well as acts as a baffle to reduce plasma backstreaming back into the fuel source. In my design, this also serves as a dual purpose of shielding the magnet. So the magnets that I'm using are samarium cobalt. These are higher temperature than your typical neodymium magnets. And they're often actually used for permanent magnet style Hall thrusters. So again, this gas baffle goes right in over the magnet assembly, which is used to distribute the gas up into the channel and also protect from plasma backstreaming, as well as thermally shields the magnet. The magnets are good to maybe a couple of hundred C at most. And in this design at these very low power levels, heating should not actually be that much of an issue. But it looks like the actual parts came out really nice. Very, very clean machining. There's a very tiny lip there. Everything looks fantastic. So that I'm very happy about that. The next part is the anode. And the anode serves as, or the high voltage is applied to initiate the discharge between the electron source and the anode part itself. So again, here you can see the anode with the anode feed. So this is the anode. It is very, very tiny. I'm not sure if you can see it. There's a little channel here I left. This will be for either brazing or spot welding a feed wire that goes in. So you have gas baffle, you have the first insulating washer, then you have the anode piece which fits right over top, and then the next portion, so a tiny little stack. And one of the challenging things again about this entire design was being able to mount the anode in such a way that allows it to be insulated from the housing and allow me to actually feed it in without having to worry about any bolts or anything holding it together. So underneath the gas baffle portion, there's actually a tiny wave spring that is used to compress the entire assembly against the upper cap piece. So now that we've got the major parts, and again, really, really happy about the quality of these pieces. I'll just kind of put them here to go over a little bit of assembly more with the big parts. So now we can get on to the main part. So this is the thruster body and the cap piece, and I'll kind of explain more the functionality of how this thruster operates. This operates very similar to an anode layer thruster, or not anode layer, stationary layer, but with a little bit different principles. So let's see, we have the two major pieces. Now these pieces, the baffle and the anode are both made from stainless steel. These two pieces are actually made from 1018 steel, so very, very high iron content, because I need the iron in order to complete the magnetic circuit for the operation of the thruster. So again, for those of you who are just joining or have been here, there is a live chat where you can actually ask questions during during this at any point. So let's actually take a look at the main body now. So let's get this guy opened. Now, everything looks good on some of these. This particular piece has a lot of threaded holes, so I'm really hoping that I actually spec'd all these holes properly, because because I'm not exactly sure. I'm fairly confident that everything came out well. And looking at the other parts, I'm really happy with the machining from Xometry so far. It's been really fantastic, and I actually got these from ordering to shipping here with the economy option. It only took about 3 weeks. And some of these parts are a little bit more complicated, especially the main Hall thruster part. Let's get this guy open and see the first look at the first applied ion system Hall thruster. So, got this guy. Looks like it's going to be pretty oily. Again, because it's steel as opposed to stainless, I'll have to be a little bit careful with it. So definitely going to need a lot of cleaning. I'll just grab a Kim wipe. Just because things are going to get a little bit messy. But let's see how this guy came out. All right, let's toss this. So this is looking absolutely fantastic. I'm really happy with this. I'll give a close-up after I kind of cleaned it off from the machining oil a bit, but the finish looks really great. It looks like all the holes are in fact tapped. Everything looks there. Side pocket for the anode feed is good. So this is looking really good, and I'm very excited now to actually start getting this system together and firing it up. So here we have the EHT1 Hall thruster head assembly. So this is a little bit different. Again, in order to make the system very compact, the Hall thruster head itself, which is this portion here, is mounted directly to the gas distribution plate. So this plate fits right on top of the actual thruster itself. So if we go back to the Hall thruster diagram, you can see that the head goes right on top of the fuel distribution system. And right next to it, we have the feed for the hollow cathode assembly. So again, the Hall thruster, the gas distribution, and the hollow cathode are all integrated into one piece to allow me to make this as small as absolutely small as possible. So let's see if we can get a better look at this. So you have a bunch of little gas distribution holes inside. This is kind of the back where the feed is, and there's the gas port for the hollow cathode side. So Kenny B is asking if I've had any success with PLA printed parts. PLA, there's a few things about PLA that I've avoided. One thing, for any of the plastic materials that I use, they have to be high vacuum compatible, and PLA is a great prototyping, a very low cost prototyping material, but it's very low temperature tolerant. It has kind of low dielectric strength compared to the like Ultem or some of the ceramic embedded stuff, and it's not as high vacuum compatible. Ultem, Peak, Teflon, those are like really the top grade vacuum plastics because they have very low inherent outgassing. And I have found in some of my other thrusters that outgassing can be a real challenge, especially with high voltage. If you have a gas source in vacuum and you have high voltage, you're going to have something that's going to break down. And PLA just doesn't have the mechanical or the vacuum or the thermal properties that I really need. And even with some of this stuff, I'm really pushing it for the 3D printing. For some of my other designs, I've had issues with high voltage actually breaking through the layers of the prints, even with the Ultem. So not breaking through the Ultem material itself, but actually straight through the layers, which is why I'm trying to move towards the ceramic embedded SLA, so that it's completely solid, completely uniform, and there's no gaps or anything for electricity to kind of snake its way through. Because things get really weird in vacuum with high with high voltage, and they go places where you don't really expect. So great question by Kenny B. So for the thruster, you can actually see there's the threaded holes around here, and then alternating are holes for the permanent magnets. So the permanent magnets actually go inside each of these holes. There's 7 around the periphery, and then there's 1 in the center. So if we go back to the design, you can't really see the in this particular cross section, you can't actually see the magnets on the side, but essentially, if we kind of draw out the magnetic field lines, the magnet has north and south poles, and then at the top, essentially, if you can envision the magnet inside the body, you have the north here and the south here. So this kind of creates magnetic field loop going up and through and around here. So you kind of have magnetic loop, and this top pole piece kind of focuses that in through this area, kind of right around the system. Now, what's the purpose of this magnetic field? This magnetic field actually helps capture electrons and extends their orbital paths inside the thruster to increase the amount of collisions that happen with a gas. So the more collisions you have, the more chances of ionization. So it makes it easier to ionize the gas and makes the overall system more efficient. So let's say you have either some neutralizer source, or if you have like either a filament or some sort of hollow cathode on the side that's spraying out a plasma. So you will have electrons coming from these sources, so either boiling off the filament or coming out of the plasma plume on the hollow cathode. So these electrons, some of these electrons will actually get entrapped in to this area, ionize the gas, and then the discharge between the, which will allow the discharge to be sustained either between the plasma, so there's a plasma bridge that forms, or between the actual filament itself. So this allows the discharge to occur for the plasma, and then there's the ion acceleration mechanisms that happen after. And I won't get into the physics of the Hall thruster because that's a whole other topic, but just kind of for this basic principle, you have the magnetic field loop here, which kind of captures the electrons here, and then other electrons out here kind of are used to neutralize the beam. So again, we have the thruster. So if you can actually see the hollow cathode piece, if I'm using the hollow cathode, this sits right onto here, so there's going to be a little O-ring here to seal it. So the hollow cathode will actually sit up right next to the main head and the discharge portion. So again, this is a very, very tiny system. I think if I grab a ruler here, we are talking, the actual Hall thruster head is 20 millimeters across and maybe 7 or 8 millimeters tall, so a very, very small Hall source, and the neutralizer sits up right next to it to make this as compact as possible. Now, there are some interesting effects that might happen with the hollow cathode so close to the head, and this is going to be kind of one of the interesting and key challenges going forward with this discharge, is seeing how this affects the stability of the entire system during operation. So now let's actually get to the cap, and this again is used to kind of complete the magnetic circuit of the thruster and kind of direct the magnetic field lines down towards the interior portion of the thruster head. So this is going to be a bit oily as well. This is also steel. And let's open this up, clean it off, and then get a good look at kind of the more complete assembly. Very simple, there's no threaded parts. The bolts just go directly through and thread right into the Hall thruster head. So clean this off, and I'm going to probably want to not touch the plastic parts. They will be fine with acetone and alcohol, but just to make cleaning easier for the final assembly. So here we have the cap piece of the Hall thruster. So this actually goes directly on top to complete the magnetic circuit. So you can actually see that's kind of what this system will look like. And then you'll have the anode feed part that goes here and bolts onto here, and then the hollow cathode part. And if I'm using the tungsten neutralizer, this part will be blanked off, and I actually made it so that way I just have a simple ceramic standoff on this hole, and then some different mounting hardware to allow for the neutralizer portion there. So why don't we actually kind of do a preliminary assembly of this thing. So we have the Hall thruster head itself. We have the little spring that goes in to compress the assembly. Next, we have the gas distribution baffle. So before I put this in, I would have to put the magnet in, but I don't need to really do that at this point. So the gas distribution baffle fits right over top. Looks like I got my tolerances actually pretty good this on this first go. So that was kind of one of the things I was worried about, is if this would get stuck. But I oversized the tolerances a little bit just to make sure, and then on the next iterations I'll kind of clean it up to really tighten things up. Then we have our standard ceramic washer. This is again straight from McMaster-Carr. So this part goes right in here. Next we have the anode. So before I do any final assembly, I'll have to figure out how to attach the feed wire to this, either brazed or spot welded. So this guy goes in like that. Then we have the final ceramic piece. So there's a little bit of height, which allows me to compress it down with the cap. And then finally we put the cap piece right on here. So you can actually see this is the assembly of the Hall thruster head again. So again, this entire thing is meant to be extremely simple, extremely low cost, and really play into the limitations I have with my very limited funding and manufacturing capabilities, to be able to scale this technology down to very small satellite classes. So again, we're looking at the 3U, 2U, 1U class satellites, and with the next version, the AIS-EHT1, which is a lower class power version, that will use an anode layer type configuration, so a modified version of this, which will actually aim at neutralizerless operation. So at the very low power levels that I'm looking at for that one, 5-watt class and under, there are some special things that I can kind of exploit with the operation of anode layer sources that would allow me to do self-neutralization of the beam, which is actually a known property of anode layer sources in industrial processing. At higher power levels, you'd have to go with an external cathode, but at very low power levels, you can actually get self-neutralization of the beam, essentially operating at very high voltage, low currents. You get a lot of secondary emissions from the casing, which is used to neutralize the beam itself. So here we have the Hall thruster assembly again. So kind of if we put the neutralizer cathode on, and then, well, it'll be a little bit difficult to do this without the bolting, and I'll have to bolt it up afterwards. And then we have the anode feed portion, and everything looks like it fits great. So this is going to be the complete Hall thruster head, which once all assembled and bolted down, we have the heater portion again, which bolts directly to the gas distribution valve. And then finally we have the thruster head, which sits on top. So this is the complete AIS-EHT1 Micro End-Hall Thruster assembly. So again, extremely tight integration with all the subsystems. The fuel delivery, fuel management, Hall thruster, and neutralizer. Both the Hall thruster and neutralizer are fed with the same exact gas source. So both of them are mounted to the same distribution plate. And that allows me to do this design without the complex valving. It allows me to scale it down. A lot of times for very small CubeSats and pocket cubes, actually especially for pocket cubes, you can't run any pressurized propellants. So that eliminates a lot of options for conventional technologies. And my goal for the ADAMANT series is to really open up these technologies, like Hall thruster technology, gridded ion, RF plasma, the same type of solid unpressurized fuel with relatively non-toxic and non-corrosive fuel that really allows these small CubeSat groups, nanosat and picosat groups to explore these conventional technologies that would normally not be available otherwise. And again, for these types of systems, I'm going for very simplified manufacturing, very low power, so it allows it to be accessible and really affordable for these teams. So typically, you're not going to find Hall thruster prices, just out there floating. But typically, with how the field looks, it's probably on the order of $100,000 and higher for a Hall thruster system. And these systems are very, very big. There isn't really anything that scales down yet to this particular class. There are some companies out there that are at the 50 watt, 100 watt, and stuff, but that doesn't quite really allow you to get to the extremely small end. Now, when people talk about Hall thruster scaling, there's a lot of inefficiencies that evolved, and for this particular technology, the smaller you go, the more inefficient it becomes. However, if you look at some of the literature that's been done at this scale, which is there has been a few Hall thrusters built at the 5 watt scale, you're getting thrust to power ratios of up to 20 micronewtons per watt, which doesn't sound like a whole lot, because if you look at the high power Hall thruster classes, you're looking at 50 to 70 micronewtons per watt. So you do see a decrease in inefficiency. However, if you take into account the power that's being used at this scale, as well as the thrust really needed, especially in low Earth orbit, you actually don't need that much thrust in order to do a lot at these low Earth orbits. So 20, 30 micronewtons of thrust will actually do quite a bit for these smallest class of CubeSats. And if you look at some of the other technologies being produced for these types of satellites, if you look at vacuum arc thrusters, pulse plasma thrusters, electrospray, you're seeing thrust to power ratios anywhere from 5 to for some of the better stuff, 35, 40 micronewtons per watt. So in terms of scaling, it actually fits very nicely with some of the other technologies that are being developed at this scale. And in terms of ISP, again, that depends on that very widely in electric propulsion. Very tiny subjoule pulse plasma thrusters will be at a couple hundred seconds, whereas FEEP, which is the liquid metal ion thrusters, will be several thousands of seconds. So we got a question again from Kenny B. Do you see yourself being able to procure a space on a ride share and potentially test this in space sometime in the future? So actually, that's a good question. One thing that's kind of unique about the Applied Ion Systems effort is that I work very closely and very openly with the CubeSat and Pocket Cube communities, and these communities are fantastic because they're very fast development, very hands-on, very iterative, and they're overall a really great community. And you're seeing a lot of efforts pushing to scale technologies and make things more and more advanced and more capable. And actually, I have currently delivered 4 thrusters already. 2 of them have already been integrated onto satellites, the AMSAT Spain Genesis and an L Pocket Cubes. So this is the Micro Pulse Plasma Thruster. This is the GPPT3. This is kind of my most iconic thruster, if you will, if I had an iconic thruster. And this is the most tested thing, but there are 2 of these already currently on satellites right now. The launch has been delayed over and over and over again. Hopefully we're looking mid-March to be able to test this. And I also just recently delivered 2 more of these in the past month. I can't say the group yet, but we're looking to potentially test another one of these pulse plasma thrusters on board their satellite as well. So really at the scale in the field, in terms of propulsion companies, there's no one else really tackling. Well, there are people tackling propulsion at the very low and small scale classes, especially in terms of like electrospray technologies, but these technologies are still extremely expensive. For pulse plasma thrusters, you're looking at a starting cost of around $25,000. For electrospray stuff, you're looking at an average price of around $50,000. And for a lot of these small groups, I mean, that's either the entire launch cost, that's more than the entire satellite cost, and it's just not feasible. So what I'm doing is working very closely with the community to develop propulsion systems at an order of magnitude or more reduced costs that allows them to explore these propulsion systems, making it super bare bones, super low power, super compact, very simple, to really open up these options for a lot of these groups who are doing some really amazing work and expanding and pioneering the space field at the very small satellite scale. So hopefully with testing of this thruster, I am looking to offer it. The GPPT3 is also available, and I build that. I do vacuum testing and I ship it out. So any nanosat team can go ahead and actually get those systems, and I can work with people to develop or tweak things as needed. But I do plan on offering this particular thruster system to the same kind of power and size class of nanosat groups out there, and hopefully if this works, it will open up some opportunities for potential testing in the field. The Pocket Cube field in particular is very good because there's a lot of launches coming up. Things are iterated very fast and are lower cost than Cubesats. This particular technology is going to be quite a challenge to scale down to the Pocket Cube level. It's almost there. The Pocket Cube standard is 5 centimeter by 5 centimeter, whereas the Cubesat is 10 by 10. So scaling this down is going to be really challenging. The Hall thruster itself, the fuel delivery system itself, are already at that scale. I can actually squeeze this down a little bit more and optimize the design for the Pocket Cubes. But the really challenging part is going to be scaling the valving technology down for that. And I think out of everything for the ADAMANT series, the valve is going to be the most challenging thing. I've already kind of proven the concept of the sublimation feed for Adamantane. I'm pretty confident that the Hall thruster itself will work, but the valve is going to be really challenging, and that's going to be the big difficulty in scaling this further. But hopefully if I can scale this down to the Pocket Cube community, that'll also open up a lot of opportunities for launch and testing in space. And especially with Pocket Cubes, you're seeing systems now come out with anywhere from 5 watts to 20 watts of available power, which is getting into small CubeSat class power levels being generated. So they can actually be able to handle propulsion now. It's just there's been almost no work on propulsion at that scale for these types of thrusters. So I definitely foresee that this stuff will actually be able to be integrated and tested. So the faster I get this stuff tested and running, the more chances I think will open up. And this system is actually almost ready to go. I'm waiting on a couple of more pieces of hardware. They won't be in by this week, but next week they'll be in. and I am looking at the potential first ignition tests of this thruster by next weekend, possibly. So I will actually be doing a full live stream of the first ignition test of this thruster. All my tests are being are live, either live tweeted or live streamed. But I'm going to do a kind of a more official setup with this thruster, kind of on the YouTube channel, and really, it'll be a pretty exciting event, because this will be the first applied ion system Hall thruster, and Hall thrusters are obviously pretty cool. So it'll be very cool to see this small Hall thruster, hopefully in action. I can't guarantee that it'll work, because the first time for any design, there's always some unforeseen issues, but I'm crossing my fingers, and hopefully we'll see some plasma plumes coming from the thing. So Kenny B is asked for another question, and no worries, I'm here to answer questions, and that's kind of why I'm doing this live feed, because you will find that the electric propulsion field is very stealth and secretive about designs. I mean, you can find these designs and everything and information kind of in literature, because a lot of companies start out from academic spin-offs, but there's not as much open engagement in the field about the technologies. And one of the things I want to do with applied ion systems is make these systems more accessible, not from the standpoint of just low-cost systems, low power, very small scale, but I want people to really understand and have a view of what goes into these systems, and really engage people at a level that's just never been done in the electric propulsion field with traditional companies. So in particular, what about the valve that makes it especially difficult to scale down? Well, it's really the size. I have to try to keep the entire size of the system as compact as possible. And really the best way to integrate that into the entire assembly is keeping it in line between the fuel delivery and the thruster head. So it has to be very flat form factor, which means that I have to have a very small motion of the valve, and there really isn't any options that I've seen that fit what I'm kind of looking at. You have your traditional valves with the lines and everything, which work great for external tanks. So you have your tank mounted, you have your thruster, your neutralizer, and then you have the valve feeds and everything for that. But for a system as tightly integrated as this, I really have to go with something that's just streamlined into the design. And since there's nothing really out there, I have to kind of make my own solution. So it's the challenging thing is going to be keeping the size small while actually having the valve open enough that I get actual usable gas flow. The other thing is finding an actuator technology that'll fit the size and power requirements that I need, but also have kind of the pressure hold off as well. This is an unpressurized system, so the valve isn't going to be acting against any pressure. Even if there's sublimation, it's going to be very, very low, really negligible pressures. But the challenging thing is going to keep the valve from leaking. This design, I've already found a whole bunch of flaws in it, and I already have a second design, so I'm going to wait a little bit longer for funding to do that. So for the upcoming Hall thruster test, it will be the entire assembly, but the valve will not have the piezo element inside, so it'll just be stacked and essentially be in the open position. So that'll actually kind of allow me to see what type of gas flows I'm getting at ambient conditions and then with the heater power. So that's going to be definitely the most challenging part of this build for sure, just because of the constraints I'm working with. And already with the bender elements that I'm using, trying to fit it in, last week I actually shattered it into 3 pieces because this is still kind of a delicate thing, and the tolerances on this were spot on, but I made it so tight, and I found out the hard way that trying to tap it in with a hammer is not the way to go. So I'm going to have to order a new one of these and adjust the design. And really, I think the valve is going to be the key constraint of the whole design, because if it leaks, then you're going to have some sublimated adamantane fuel eventually leaking away and just going off, which would not be good, because if your satellite is sitting waiting for a long time, you're going to deplete the gas before it's even launched. So I have to make sure that the valve is fully sealed and seated, and qualify that really well. And that'll actually be pretty simple to test, because I know that my vacuum system really struggles with any gas load for this particular fuel source. So if I can actually pump down to my normal operating pressures of about I'm hitting mid 10 to the minus 7 torr now for testing for my pulse plasma thrusters and electrospray stuff. So if I can hit those levels with the fuel loaded up and the valve down, then I know that the leak rate is going to be really, really good. And anything higher than that during pump down, I'm going to know that I have some sort of leaking, and I can back calculate kind of the leak rates involved with the system. So yeah, and again, I appreciate everyone's support with this project. It's not always easy to be super open with these developments, and starting out, there's a lot of people saying I should look at patenting things, and tech patents are just cost an exorbitant amount in the U.S. to begin with, so that's not really an option. But I really want the systems I design to be very open and accessible to anyone, and it really fits my philosophy with the whole maker community and sharing the knowledge and resources, because at the end of the day, it doesn't do anyone good if you're just hoarding away all this knowledge and nobody can learn from it. So I'm hoping these developments, and especially getting into stuff advanced as Hall thrusters. When I first started this effort, I immediately started with pulse plasma thrusters because they're very simple, they're very cheap, and Hall thruster was really the last thing on my list, just because coming in, it's just always put on this super high pedestal. It's like the ultimate thruster in the field. And, I always thought it was an extremely complex system, and the whole issue with the pressurized fuel and valves and everything made it out of reach for me until I came across the adamantane fuel, which allowed me to do sublimation testing very safely, and allowed me to scale this technology down. And I want to show that these types of technologies, the electrospray, the Hall thrusters can be done and accessible even with minimal resources and budgets, and really open up the accessibility of these technologies much more outside of conventional development through academic grants or multi-million-dollar funding. I'm really glad to hear that you've started development on your own pulse plasma thruster, and my efforts have kind of inspired that. That's really, hearing that really makes all this definitely worth it, is to see others to be inspired and start exploring these systems as well, because there's a whole community of vacuum hackers out there. There's tons of people who do high vacuum technologies at home, from semiconductor manufacturing to neutron sources, plasma systems. So the vacuum aspect of it is really accessible at this level. And these technologies, like Hall thrusters, are nothing more than just a type of ion source. Pulse plasma thrusters are nothing more than just a type of pulse plasma source. And these systems have been around for many, many decades, and they're very, very old technologies. I mean, a lot of people, when you see articles and stuff about some new propulsion system or ion thruster, it's always made out to be this incredible sci-fi magic, cutting edge, super inaccessible, only NASA type stuff. But the reality is, all these thrusters are just modified plasma and ion sources strapped to the backs of satellites. And these plasma and ion thruster sources have been used for decades in many fields, in manufacturing, in industry, in particle physics, plasma physics, and they're just adapted to just providing some sort of reaction to make a satellite move. And when you break down the technologies, you'll see that they're essentially, they all share very similar characteristics, and they're not as difficult as all these kind of hype articles make them seem out to be. Like for pulse plasma thrusters, for example, they're literally just flash camera circuits. If you look at a disposable flash camera circuit and you actually look at a pulse plasma thruster circuit, and if you take like the GPPT3 example, which I have the design files on my website, you'll see that it's literally practically a camera circuit. You have your anode connection, you have your cathode connection, which is has a high voltage capacitor attached between the two, and then you have the igniter. And for the igniter, I am literally using a flash camera trigger transformer. So if you actually take that thruster head out and you put in like a little xenon flash tube, you can probably fire it the same exact way. So a lot of these systems all share very common and basic principles to many other technologies out there. And I want to show that these systems are not as complex and difficult to do as they're made out to be. Now, granted, I have a ton of failures. Things break all the time. I fry things. Vacuum testing can be absolute hell when things go wrong and I'm trying to debug. So it's not easy from the standpoint of actual testing and getting things wired up and firing properly. But from the technological standpoint, the accessibility standpoint, this is stuff that can and actually is being explored by now people in their basements like myself. I'm kind of really one of the first in the community that I've seen to really be pushing heavily and exploring plasma and ion thruster technology. This stuff is really not much different from a lot of other technologies you see people exploring. So it's all the same basic principles. It's just slightly different applications and form factors. So that's kind of the basic overview of the Hall thruster system, and a really big overview of the ADAMANT series and some of the stuff in store that will be coming. So again, all the tolerances on this came out absolutely fantastically. I'm super happy. Definitely will be going further through geometry to get everything else manufactured. This was really a testament to just really how good the services are. And if all this stuff checks out and I get ignition with this, I have the AIS-EHT1, which is the anode layer source. The design is all set and ready to go, and I'm just waiting to do some tests on this before I start cutting metal. So we could potentially be seeing a second applied ion system Hall thruster design started within the next month, in addition to the testing of this system. Now, for testing of this system, I'm going to break it up into a few parts. I'm going to do testing with the filament neutralizers. So I just got some tungsten filament that I'm going to be using for the initial neutralizer. And then I'll be testing the hollow cathodes separately. And once I kind of get those things operating well by themselves, then I'll combine the two systems together and really see what this thing can do operating nominally. Now, the other issue I'm going to have is my vacuum system. I can run these systems still, but the pressure arises to a point of where I can't really take accurate thrust and ISP measurements just because the background gas collisions are going to mess up those measurements. So I can do ignition testing, I can do some lifetime testing, but until I solve my pumping issues, which is really just being able to handle the large gas load coming from this thruster, like with the pulse plasma thrusters and the electrospray stuff, the gas load is really, really small. So I can pump down, I can stay at 10 to the minus 7 torr and fire the thrusters and not have to worry about the pressure rising. But for this system, it's very, very challenging, and I may even have to move to some sort of cryo pumping, which I'm actually exploring potentially installing my own very simple liquid nitrogen cold trap type assembly, which will just be made from basic standard off-the-shelf vacuum parts, and see if that will help with my pumping speeds. That won't be for a while, because I really want to get this thruster started firing and testing and explore the valve and fuel delivery more. but that will be something to do before I can actually do more official qualification of the thruster system, of the actual thrust and efficiency measurements. So there will be, this is kind of a test, somewhat of a test live stream going forward. I will definitely be doing more of these, so I will be doing another live stream on the GPPT3 system. So my first system, I'll break that down, show all the different parts, go over the schematic and everything for that. I'll go over the electrospray stuff, which is quite hyped in the micro EP field, and kind of break down how I approached being able to do ionic liquid electrospray with minimal resources. And then once the anode layer Hall thruster comes in, I will be doing an unboxing and breakdown video of that. And of course, tons of upcoming test videos, especially with the Hall thruster. Again, I'm pretty confident that I will actually see some stable controlled discharge, just because adamantane seems to ionize extremely well. I was getting very stable, and there are videos already up on the AIS YouTube showing the various discharge cells operating from 3/4 of a watt to 2 watts of discharge on the adamantane gas. So I am fairly confident that I will get some discharge at a very, very low power level. And once this has been tested and qualified, then I'll actually start working on the electronics for this system. So the electronics will be very, very simple. There will be just high voltage power supplies for the discharge, for the neutralizer, for the piezo valve eventually, and then a very low voltage supply for the heater, which I might not even have to use that much, just because the adamantane sublimates so readily at pretty low temperatures. Again, I want to thank you all for taking the time to view this live stream and overview of the thruster. If you have any other questions, you can definitely reach out to me. I'm always open for talking electric propulsion on the Applied Ion Systems media, social media. So Twitter is where all the action happens. I post things pretty real time as they happen, with builds and pictures and updates there. And then I'm going to start doing more live streams with the YouTube. And then the Applied Ion Systems website has, design files, has specs, a lot of information and documentation for all of these builds. And of course, you can always reach out to me through email or LinkedIn or whatever. I'm always happy to talk propulsion, and never really turn down people who are willing to engage and ask questions about these technologies. I talk with everyone from high schoolers to seasoned veterans about this stuff, and I think that's one of the things that makes the AIS approach kind of different from other electric propulsion companies out there, is the openness to just engage with anyone and show these technologies, not only what I'm doing in high detail, but go over the core fundamentals of these systems and really share whatever knowledge I find for these systems, and make it available for others to make it ultimately more accessible. If there are no further questions, I guess we can finish up this live stream. And again, you're more than welcome to reach out to me and ask questions about this design, and there will definitely be a lot more updates to come, and I will be hopefully scheduling the first tests of this thruster very soon. So there's a lot of exciting stuff to come. This is a very unique effort. I mean, this table is literally where I do all my assembly and testing for stuff on the bench, and half of the room, which you can't see, is literally storage for laundry and parts. So my resources are and space to do all this stuff is pretty small, but we're definitely making some really great progress. And again, I have to really thank everyone who supports this on Twitter and through Patreon. And if you like the developments that I'm working on and want to help contribute to open source propulsion, you can contribute to the AIS Patreon, which helps sustain a lot of these developments on a monthly basis. And especially through last year, with the electrospray and a lot of the pulse plasma thruster stuff, I wouldn't have been able to develop and do as many tests without the amazing support of everyone. So that's really helped sustain this effort and show that these systems can be done without millions of dollars, without huge facilities, and hopefully it'll be a fun ride for everyone along the way. So thanks again, everyone, and hope to see you next time during the next live stream, which I will post updates for. So looking forward to some really cool plasma and ion shots of this thruster, and see you all again next time.